Okay, this talk is about number theory, and in particular about a theorem by Pierre de Fermat from the 1600s, which has kind of been kind of a special interest and like has almost this magical quality to me because it just seems like pretty amazing. So it has to do with certain prime numbers that are equal to the sum of two squares, and it seems kind of very surprising that, I mean, prime numbers are about multiplication and it's like involves the idea of addition. It's all kind of combined into some very unexpected, well, to me it's a pretty unexpected result. So I just thought it's worth starting with just taking the first few prime numbers and seeing how this works out. Like, for instance, 2 is 1 squared plus 1 squared. Is 3 the sum of two squares? Yeah. No, it's not. Okay. Is 5 the sum of two squares? Yeah, right? It's 2 squared plus 1 squared. Is 7 the sum of two squares? Yeah. No. Is 11... It's not, actually, as far as I... All right, now 13 is 3 squared plus 2 squared. 17 is 4 squared. 19 is... no. 23 is... I don't know. 29. 5 squared plus 2. 31. No. 37.
5 squared plus 4 squared?
No. 6 squared plus 1. 41. Right. 25 plus 16. 43 is... no. 47? No. 53. 7 squared plus... 49 plus 4. Yeah. 59. I don't think so. 61. This is the one I always stumble over. So they're starting to get like, it's I think it's 36 plus 25. Right, 6 squared. Okay, so these numbers, well, we'll leave out 2 because I'll explain pretty soon why 2 doesn't. It sort of works, but it's not really part of this whole idea. So, starting with 5, this one is okay. This one is. And I don't know if anybody can see what the connection is between all these numbers that I circled, or maybe you already read ahead, but. They all have something in common. It's should I break the suspense? Okay. Okay. The theorem is, the statement of the theorem is an odd prime that gets rid of 2 right there. Actually, and 2 is not of the form 4k plus 1, so it probably wouldn't fit anyway. But an odd prime p can be expressed as a sum of two squares if and only if p is of the form 4k plus 1. So the numbers we saw before, like 5, 13, 17, what's the next one? 29 is, right? So that's what connects all these numbers that are the sum of two squares. That's Mr. Fermat there. Monsieur Fermat. Okay, a little bit of history of this theorem. And that kind of strange-looking guy is not Fermat. He's someone, I don't know if anybody ever heard of Albert Girard. I think he was a Dutch mathematician, but 15 years before Fermat thought about this theorem, and maybe he even stole it from, who knows, from Mr. Girard, but Albert Girard was apparently the first mathematician who came up with this idea. And Fermat, I think he added some bells and whistles to it. He generalized it or something, but I think, as happens quite often, a famous person sort of magnetically attracts like discoveries like that are attributed to him, even though maybe he didn't really discover it. Okay, so, but neither of them proved it, or if they proved it, they never wrote down the proof. So the first proof was by Euler around 1750, and apparently, like a lot of these things, there's Wikipedia articles. Apparently, it caused him quite a bit of trouble, and as you'll see later, there's some more modern methods of approaching it that seem to streamline the proof of this. But he apparently spent quite a bit of time on this, but he did figure out a complicated proof. Later on, the proofs get shorter and shorter, but the kind of math background they expect from you is more and more advanced, and very quickly things got out of my depth. So I'm going to stay at a pretty elementary level. Okay, this is kind of how I, a little bit of the history of how I encountered this theorem, and some of the reading I did. I'm sure some people have heard of this book by Hardy, Mathematician's Apology. It's not really a book about, it's not a math book in terms of like a regular textbook, it's just it's like an essay, and it's kind of a little bit of a sad book to read, because I think the first sentence is, it's a melancholy thing for a mathematician to find himself writing about mathematics, because he felt like once he was past his 20s, I think he felt like his better days were behind him, and all he could do now is just kind of write philosophical stuff or whatever. But he did mention this theorem, and he said it's ranked very justly as one of the finest of arithmetic. Unfortunately, there's no proof within the comprehension of anybody but a fairly expert mathematician. And I sort of took this at some point as a challenge, like, even though I'm not an expert mathematician, it seemed like a challenge to try to conquer this. So, and then for a while I was reading this book by Davenport, which is a kind of a classic in its field, I think, and it's great. But I read a lot of the background to the proof, and when I got to the actual proof, which I think is pretty much Euler's proof, it just seemed pretty thorny and kind of difficult, and involved like not infinite descent, but a kind of iterative process that I just seemed like I may go back to it and see what he was really trying to do, but it wasn't something I could really grasp too easily. By the way, if anybody has questions or comments while I'm talking, it's fine to interrupt, because it might even get me more relaxed here.
How do you present the proof? We just discussed that.
I'm sorry?
How do you present the proof?
No, he just discussed it, right. He just kind of used it as an example of like the beauty. The book is sort of about the beauties of math as distinguished from, practical things. Of course, he didn't realize number theory would be used later on, probably for encryption or whatever, but that was later. That was before that happened. Okay, then a couple of years ago, I came upon this paper by I forgot her first name. It's like an Indian name, but she wrote it, I think, as an undergrad at University of Chicago, and it's not, doesn't have anything original in it, but it presented a very nice exposition of a way to attack this whole issue of Fermat's theorem that just seemed to it certainly worked for me, and so that's the way she did it, using two other theorems, which I'll get to like a stepping stone. Worked for me, so that's the way I'm going to trace it through today. But almost everything that involved with this proof uses modular arithmetic, which is first of all, I mean, as everybody probably knows, number theory deals with basically whole numbers, integers, usually positive integers. And the usual analogy to the first time you explain it to somebody, it's like, this is what happens with a clock, because once you get to 12, you don't go to 13 unless you're European, and then it's a 24-hour clock. But like I was just in Spain, and of course anywhere in Europe they routinely use 24 hours. But whatever, it's a cyclical idea that once you get to a certain number, you just start all over again. And so a traditional clock uses 12 hours, which is kind of convenient, because why 12? Well, one nice thing about 12 is, hi, just have a seat, is it can be divided by a bunch of different numbers, so you can, divide 12 into 6 parts, into 4 parts, into 2 parts. So it's kind of a friendly kind of number if you want to be symmetrical and even about things. So, but if you for instance look at if you start at 12 and look at every third number, let's say you go around this way, you get back to 12, and then you go back to 3, you go to 6, you go to 9, if you go every 3 numbers, you're going to endlessly just keep circling these 4 numbers, and you'll never hit the other numbers at all. So this is an example of a number that's very much definitely not a prime number. Now, I just made a small change in the clock here. I just, sorry for the drawing. It's not very, maybe Michael, maybe you can help me later on figure out how to make some of these drawings more symmetrical. I was still struggling with this here. So anyway, but if I did it right, it has 11 numbers. So I just took one number out, and that makes quite a bit of difference. If we do the same thing we did on the last slide, we'll start at the top and go 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3, 3. Okay, so I've done 11 circlings, and each one has been a different number, and I think this is sort of a cool thing to show like kids, because it's like, seems almost like magic or something. It's still kind of freaks me out that this happens, but so I sort of made up this silly little slogan, but you could say that prime numbers play no favorites, because once you do this 11 times, you hit every number once. Then of course when you keep going, you're going to go through the same, you're going to be starting the same place, so you're going to go through the same thing again. Okay, so why is it that, and this concept I think is pretty important for what happens pretty soon when you get, so why does this prime clock act in such an impartial kind of a way? I think you need a little more, I want to give you a little more background about this first, because I think it'll help. The first thing is, let's get this out of the way. There's something called Euclid's Lemma, which of course goes back to the father of geometry, and he did other things too. So if you're given any prime number p, now this symbol here means divides. So if p goes into the product of a and b, any two numbers, then either p divides a, goes into a without a remainder, or p goes into b, or both. And if you look like in Wikipedia, you'll see some kind of a proof of this, but I didn't pursue that because I think I can see this intuitively, because a prime number doesn't have any other factors except itself, and 1, of course, but there's no way you can split up a prime number between a and b, so it would have to go into either, at least one of them, evenly. Does anyone have a problem with that idea? Or because it seems pretty, to me it seems pretty self-explanatory. No, okay, good. Now, underneath that is like the counterexample. 6 is not a prime number, and let's say you consider how 6 goes into 3 times 8. Now, of course, 6 doesn't divide either 3 or 8, but 6 divides the 24, which is the product, right? So the reason that can happen is that 6 has a factor of 3, which goes into the 3 once, and it has a factor of 2, which goes into the 8. But with a prime number, that'll never happen, right? So that's the difference. And then underneath here, there's an extension of Euclid's lemma, sort of a generalization, or it's, well, I don't know what you call it, but instead of a being a prime number, if a goes into b times c and a and b are relatively prime, which means they don't share any factors, then a has to divide c. And that also comes up later on, I think. So I hope this is all kind of makes sense, because
There's a result, there's a result, I think, available by induction that every integer is uniquely a product of powers of primes. So like 2 to the third times 5 to the second times whatever. And so sometimes one way I visualize this is if you have an integer, you can have like a set of heaps, like the heap of 2's and the heap of 3's and a 5 and so on. So this says if you have like a single bead, it has to come, and you're like bringing 2 sets of heaps together, that, bead prime has to come from like one or the other, or you can take it from both. But if you've got a composite, then its beads can happen to be split up among A and B. I don't know if that was more or less helpful.
that's what's called the fundamental theorem of arithmetic, right?
I think
that,
so, yeah.
that any number is expressible as a unique combination of powers of primes. I think that's what. Yeah. Right. I'm not sure I ever quite followed the proof of that, but again, it's like, well, I guess that isn't quite as intuitively clear to me as this is, but.
Just an example that I couldn't remember, but I just looked at my phone. So you have the integers, and you also have the square root of -5. So you have like a plus b to the square root of -5 for a and b are integers. Then among numbers of those kind, like there are numbers that have no factors besides themselves, and one of which is accessible, which is why it's a
I thought the proof in that higher arithmetic.
I'm sorry.
I thought the proof in that higher arithmetic.
Oh, you worked through that book. You
Not the whole book, I haven't finished it.
yeah. The proof of the
I'll-
fundamental theorem.
yeah, okay.
It's been a while, so yeah, I have to take a look at that again. But actually, that isn't, I guess, central to this particular theme. But yeah, I want to look at that. Okay, so all right. Okay, now the idea of congruence is really the key, I guess, the key concept for going forward here. And this will probably, I guess, look kind of familiar, but if the triple equal sign means congruent, and A is congruent to B modulo M, that just means that if you divide A by M and B by M, you're going to get the same remainder. So another word for remainder is residue. Sometimes you'll see things like quadratic residues, and it just means remainder. Okay, so quite often the useful equivalent to that first line is the mod. It's another way of saying the same thing. The modulus divides a minus b evenly. It goes in evenly. There's an algebraic way of showing the equivalent, but for now I just thought the graphic way works too. Like, for instance, if you have a number line and they're spaced according to the modulus, if let's say in this case a and b are both congruent to 2, like going up 2 spaces here, 2 units, modulo m, and I think you can see that you're just shifting over the yardstick, and if a and b were 2 to the left, they'd be exactly on the lines, but if you shift them both over equally, they're still going to be divisible by m. So that's not a proof, but it's, I think conceptually, maybe it helps. Okay, there's some, I don't think I'll spend too much time on it, but there are a bunch of theorems that you could almost expect to see at this point. They're about congruence. If A is congruent to B, mod M, then if you add the same to both sides, if you add the same number C to both sides, A plus C is congruent to B plus C. And the proof actually is pretty simple. If A is congruent to B means the modulus divides A minus B. Now, if you add C and take away C over here, you're not changing anything, but then you redistribute it this way, and then you can see right away that A plus C is congruent to B plus C because M divides the difference. There's a similar one for multiplication. If A is congruent to B, mod M, then if you multiply both sides by the same thing, they're still congruent, and the same kind of proof, M divides A minus B. If M divides A minus B, M is certainly going to divide C times A minus B, right? And then if you write it out, you get M divides AC minus BC, and that's this line here. So is that pretty okay? All right. Now, the thing about division gets a little dicier. It works sometimes. You can sometimes cancel, and if AD is congruent to BD, and D, but it only if D and M have to be relatively prime, and then you can cancel the D's out, and you get A is congruent to B. And the proof of this is M divides AD minus BD. M divides, you just take the D out. Now, by that extension of Euclid's lemma, since M and D are relatively prime, M must divide A minus B. So that's really the proof there. The last one here is a little bit different. I'm just wanting to motivate being congruent to a negative number, which is important later on. If A is congruent to B, then mod M, then A is congruent to B minus M mod M. For instance, if A is congruent to 4 mod 5, then A is also congruent to -1 mod 5. And what you're really doing is just moving over M units on the number line, so it's not going to change divisibility. But you can prove it just the same way. M divides A minus B, then M certainly divides A minus B plus M, and you rewrite that as M divides A minus B minus M. So, and the idea of being congruent to -1 is like, from now on it's going to be like a recurring idée fixe or theme here. Being congruent to -1, you'll see very shortly. Okay, now I think we can look at why you don't land on the same number twice, why this keeps, why this keeps evenly hits all the numbers. Supposing it didn't do that, supposing that for some A and B both less than 11, because you only have to worry about one cycle through, then everything repeats itself. Suppose A times 3 equals B times 3 is congruent, which means congruent just means that it lands on the same number in this case. Then by the definition, by the other way of writing this, 11 would have to divide 3A minus 3B. And you rewrite that as 11 would have to divide 3 times A minus B. Now 11 certainly is not going to divide 3. So 11 has to divide A minus B, and A minus B are both less than 11. And the only way this can happen is if A minus B is 0, which simply means that A and B are the same. So the only way you can land on the same number is if it's the same multiple, which means you're not landing on the same number. That's probably not the best way to put it. Is that okay? Does that?
Where's the last part come from? Where 11 divides 3 times A minus B and A minus B plus B.
It's Euclid's. Well, by Euclid's lemma, 11 has to divide. If it divides the product, it has to divide. Since 11 is a prime number, it has to divide just or at least one, and we know it doesn't divide 3, so it has to divide A minus B. But they're also A and B are both also less than 11.
Okay.
So okay. Yeah. Okay. Now, if you remember Fermat's, the so-called Fermat or Gerard, whatever, poor guy. I'm just rewriting his theorem here. There's an if and only if. Now the only if is the easy part to show. Okay, easier. And this will take care of the only if, I hope. Okay, so there are only two. We're thinking modulo 4 now. That's really 4k plus 1 just means if you divide by 4, there's going to be a remainder of 1. So a prime number, an odd prime number has to be either 4k plus 1 or 4k plus 3, right? Because it couldn't be 4k plus 0 or 4k plus 2 because they'd be even numbers. So we want to show that there's no way you can add 2 squares to get a 4k plus 3. And the way you show that is, this is all modulo 4 now. First of all, if you have this, the residue of a square is the same as the square of the residue, and the way you can show that is any number can be expressed as, I wrote um plus r. In other words, a certain time, the modulus repeated a certain number of times plus the remainder. Now if you square that, you get u squared m squared plus 2 umr plus r squared. Now the factor m is in both of these terms, so the first 2 terms are divisible by m, so the only residue would be from the r squared here. So it's safe to look at just the residues. So okay, there's any number is either, mod 4 is either 0, 1, 2, or 3. If you square it, the residue squared of 0 is 0, of 1 is 1. Now the residue of 2, any number with a residue of 2, if you square it, it's going to be 4, which is like the same as 0, going around the clock. And then if it's residue 3, it's going to be 9, which simplifies down to 1. Yeah, so any number squared is going to, modulo 4 is going to be either 0 or 1. Okay. Is this everybody with me on that? Okay. So just take any number you want, like 9. If you square it, it's 81 is 1 modulo 4. If you square 7, it's 49, which is 1 modulo 4. If you square 6, it's 36, which is 0 modulo 4. it's never going to be more than 1. So you're adding 2 of these guys together, and the sum of these 2 squares modulo 4 can only be 0, 1, or 2, and it can never be 3 because it just can't add up to that high. So that takes care of the only if part. So now all we have to worry about is the if part. So the rest of this, I guess, is about B. Okay. Now here's where this kind of streamlined, the thing I read about in that paper by Bhaskar. There's a nice streamlined approach to this, but we have to do a little bit of preliminary work first. There's 2 theorems we have to look at, which is Wilson's theorem and Thue's, how is this pronounced again? Thue? A Norwegian, this is a Norwegian guy, I'll get more to this later. Thue's lemma, which is really kind of a very, very weird thing, but we'll get to that. Okay, so first we're going to look at Wilson's theorem. Is this familiar to anybody, this one? Oh, right. It's pretty neat in itself, I think. I don't even remember Wilson's first name. He was, I think, a pretty obscure. He was like somebody's student, in some British guy who was somebody's student at a math. He announced this theorem, but it turns out actually that I think it was known hundreds of years earlier, maybe like Arabian mathematicians or something. But I guess he brought it up to the foreground again or something, and then it was proved a year later by Lagrange. Okay, for any prime number, if you subtract 1 from the number and take the factorial, it's going to be congruent to -1 modulo p. For instance, here's a little example. If p is 5, you take 4 factorial, 4 times 3 times 2 times 1, which is 24, which is, you could say it's 4 modulo 5, but the better way to see it for this is it's 1 short of being a multiple, so it's congruent to -1 modulo 5. And I'm going to prove it in quotes. The paper, that Bhaskar paper, has a general proof, but I think it's easier to see it first with an example. Oops. Okay. Let's take p equals 11. Okay. Now we take 10 factorial, and we want to show that it's equal to -1 modulo 11. All right, how do we write all the numbers down? Okay, 10 factorial. All right, now first we look at the outer 2 numbers, and you'll see that 10 times 1 is 10, which is 1 less than 11, which means it's congruent to -1 modulo 11. Okay, so what are we left with? We're left with 4 pairs of numbers. We're left with 8 numbers. And what I'm going to show is, what I'm claiming is, you can pairwise, you can pair these numbers up, and each pair is going to multiply out to be +1 modulo 11. Okay. So maybe somebody can help me with this, because let's look at 9, right? Okay. Now, 9 times one of these other numbers is supposed to be, let's hope it is, congruent to +1 modulo 11. Is it 8? I don't think so, right? Is it 5? Okay, good. So 45 is 44 plus 1. All right. Now, what about 8? 8. 8 times 7 is 56, which is 55 plus 1. 6 times what? 2 is 12, which is 11 plus 1, and these better work here. 4 times 3 is also, wait, 4 times 3 is is also 12. They can both be 12, it's okay, which is also 1 modulo 11. So everything inside here in the blue is just multiplies out to 1 times 1 times 1 times 1, and all we're left with is the negative 1. So that's the way it works. But why does this happen? It's the same reason that that when you go around the clock every 3 times and they all hit different numbers, you couldn't, like if 8 times 5 is 1 modulo, if 9 times 5 is 1 modulo 11, you could not have 9 times, also 9 times 4 being, you couldn't have, it wouldn't work. It's for the same reason. We proved it before, sort of. So, and there are kind of other, like, cases you might want to get, like, for instance, why couldn't one of these numbers maybe times 10 turn out to be 1? And the reason is 10 is congruent to negative 1, and if you multiply any of these others, it's not going to turn out to be 1. It just wouldn't work like, you couldn't, it would be like negative 9, negative 8. Okay. And similarly, any of these numbers, 9 through 2 times 1 would be congruent to 9 or 8 or 7 or 6 through 2, so none of those would be 1. Now, the last possibility is that some number 9 down through 2 times itself would be congruent to 1, mod 11. So let's show why that could not be. Supposing a squared is congruent to 1 mod, this would mean that a squared minus 1 is congruent to 0 mod 11, or a plus 1 times a minus 1 is congruent to 0. So this would mean that 11 would have to divide a plus 1 times a minus 1. And we know from Euclid's lemma that 11 would have to divide either a plus 1 or a minus 1. But that could not be the case, because both a plus 1 and a minus 1 would have to be less than 11, because the largest size for a is 9, and 9 plus 1 is 10, and the lowest number is for a is 2, and 2 minus 1 is 1. So we've seen that this is not possible, so a squared cannot be congruent to 1. Therefore, we've eliminated this final possibility. Okay, so that's Wilson's theorem, and this is 2A's lemma, and there's a very sober-looking Axel Thue, Norwegian mathematician, who apparently did some cool stuff. And this is a very weird-looking theorem here, but it turns out it's like, and this is probably why he developed this. It's sort of like tailor-made to work with in a proof for this Fermat's theorem. Okay, so first you have to make we'll do a little definition here. Bracket around x means it's a floor function. It just means take the integer below what's inside, and what's inside is always going to be a non-integer, like it's going to be the square root of a prime number. So an example is the floor of the square root of 5 is 2, because the square root of 5 is between 2 and 3. Okay, so that's what the bracket notation means. And the lemma states, given any prime p and any integer a that's not a multiple of p, you can find two integers x and y within the range of starting at 1 and ending in the floor of the square root of p, such that either a times x is congruent to y mod p, or a times x is congruent to negative y mod p. And I think this begs for an example. It took me a while to just kind of even remember what this all is about. So let's see. Somebody want to, let's say, somebody want to just, let's say, give me a p here, not too big. Anybody, a prime number? What is it? 5, okay. And an a is what? Anything that's not too big and not a multiple of 5. Excuse me? 7, okay. So we have to find x and y such that 7 times x is congruent to y, or 7x is congruent to negative y. Okay, so it's when I do this, it's kind of trial and error. Okay, so anybody see? So x and y have to be within the range of what? Only 1 and 2. Right? Because they have to be, because the square root of, the square root of 5 is between 2 and 3. So x and y have to be either 1 or 2. They could both be the same number. 7 times, all right, I think let's see, 7, anybody see? And 7 times 1 is congruent to 2 mod 5, right? 7 times 1 is congruent to plus, right? Okay, so is that right?
Yeah.
So x is 1 and y is... I'm sorry? Oh, there can be more than one. I think there can be more than one possibility. But it just guarantees that there's always going to be one x and one y. It's kind of a weird theorem, isn't it? But you'll see how it fits in. Okay, now to prove this, it uses, there's a fancier name for this, but I think it's Dirichlet's, what is it, box something, I forget. But this is one of, I mean, I just take this as common sense, famous last words, but finite, yeah. So if you have 9 pigeonholes, it's hard to see, I guess. There's 2 pigeons in here. If you have 9 pigeonholes and 10 pigeons, at least one pigeonhole has to have more than one pigeon in it. Is that, yeah, right? I mean,
if you have 9 holes and 10 pigeons?
If you have more pigeons than pigeonholes, at least one pigeonhole has to have more than one pigeon. Right? Okay, sorry, this looks formidable here, but this is a little bit weird. Okay, so this is the proof. You define a cross product here of, this might be the weirdest part of the whole talk here. You define this kind of cross product. You take S to be the cross product of these 2 sets, so starting with 0, not starting with 1, starting with 0, and like the theorem states, going up to the floor of square root of p, and then you cross it with itself, which means you have, each of these brackets has this many elements in it, right? The square root of, the floor of the square root of p plus 1 because the 0 is in there. And these are ordered pairs x and y. And now since the square root of p is less than the floor of the square root of p plus 1, for instance, the square root of 5 is less than 2 plus 1, right? That means, if you square each side, that means p is less than this number squared. But this is the number of elements. In other words, there are more elements in this crossing than that number of elements is greater than p. Therefore, okay, we already said, therefore S, this crossing, has more than p elements in it. So now for every of these x and y's, we create an expression ax minus y. So they're going to be more than p of these expressions. So at least two of them have to be congruent to each other, because there's more pigeons than pigeonholes, right? So these two, we're going to call them x1 and y1 and x2 and y2, and so we'll set up this congruence mod p. Now, if we just rewrite it, we can get a times x1 minus x2 equals y1 minus y2. We just bring the x over to the left and the y to the right, y1 to the right, x2 to the left side. Okay. Now we're getting to what's going to be our final x and y. We let x equal the absolute value of the difference between x1 and x2, and y equal the absolute value of this difference. And for a while I was like puzzled about the absolute value stuff, but then I wrote into one of these math boards, and I think I understand it now. I mean, we want to end up with a positive x and y. So the way you deal with it is, the theorem states either ax is congruent to plus y or minus y, which means that kind of takes care of the absolute value, because if it's the wrong sign, the minus y sort of absorbs that. This might be a better way of putting that, but is this all kind of okay? Is this hopefully this will all get recorded and put up and whatever, but okay, we're almost there. Now it's not quite there because we do have ax equal plus or minus y. There's only one thing. We included 0, and we have to show that neither x or y can actually equal 0, because that's what I just said. We crossed the zeros. It seems like a little bit of mumbo jumbo, but it seems to work. So let's suppose that x equals 0. Then the difference is 0. That means x1 equals x2. But that means that y1 minus y2 is also going to be equal to 0. So that means y1 is also equal to y2, but this contradicts our original assumption that x1 and y1 is distinct from x2 and y2. They can't both. The x's and y's cannot both be equal. So since it's a contradiction, that means x cannot equal 0. And now suppose y equals 0, which is almost the same reasoning, a little different. Then y1 equals y2, and you have a times x1 minus x2 is congruent to 0. But now we can use one of these congruence rules. Now, since a is not a multiple of p, it just cannot be congruent to 0. Therefore, it's you can cancel, and you end up with you can divide both sides by a, and you get x1 minus x2 is congruent to 0 again. So x1 equals x2, and this contradicts the assumption that these two ordered pairs are different. So we got rid of the zeros, and we're back to the original statement of the theorem. So ax is congruent to plus or minus y mod p. So I hope that's pretty clear, because this is probably the strangest part of the whole process here. And if anyone wants to be more clarified, they can either look back at this or they can go to that Bhaskar paper, which I'll post it up again. It's in some cases it is more general. Where I use examples, it uses more where I was giving just using just a particular set of numbers, it uses a more general proof. So okay, so so now we're actually ready to actually prove the actual theorem here. So there's going to be two steps. The first step is we're dealing with these 4k plus 1 primes. Now we're going to show first that for every one of these 4k plus 1 primes, there is an A. Now this is nothing to do with the A in Thue's lemma. It's a different A. For every 4k plus 1 prime, there's an A such that the square of A is congruent to -1 mod p, and we'll use Wilson's theorem to show this. And then the last step, which is pretty short, is for such a p and such an A, if they once you have the p and the A, you can show that p can be represented as a sum of two squares, and this is where Thue's lemma kicks in, and it's very elegant at that point, I think. Okay, so this is the first part. For any 4k plus 1 prime, we can find this A, and it doesn't have to be unique, but it'll find that A such that when you square it, it's going to be -1 mod p, congruent to negative. Okay, and all right. So here's another place where I'm going to use an example, because once you see how an example works, I think the general proof is easier to follow. Let's take p equals 13 now, and which of course is 4k plus 1, 4 times 3 plus 1. So by Wilson's theorem, we know that 12 factorial is congruent to -1 mod 13. So we're going to, again, write all this out, 12, okay. Now, we're going to divide it into 2 halves here. And the left side has, well, let's take the right side first. Obviously, 6 is congruent to 6, 5 to 5, all right, mod 13. On the left side, we're going to take negative congruences. 7 is congruent to -6 mod 13, or it's made clear from this end. 12 is congruent to -1, 11 to -2. Okay. So we have like a mirror images here. Like, so what this boils down to is that 6 factorial times 6 factorial takes care of all the numbers. Now we're left with the minus signs, and amazingly enough, there's an even number of negative signs, because I'll get to that. Which means that, see, there's 6 negative signs, which means we can, it all cancels to +1. So we found this magic number, which is 6 factorial squared is congruent to -1 mod 13. So what you do is, it's actually 13 minus 1 divided by 2 factorial squared, which is a pretty big number. So, but actually, as you can see that much smaller numbers work too. Like 5 squared is -1 mod 13. But the point is, you have to show that there's some A that fills the bill here. So, okay. Now, if we had a 4k plus 3 prime, which we already know isn't going to work anyway, right? But this is like another angle on it. This wouldn't work because you would have, like, if it was like 11 and you had 10 divided by 2 is 5, you'd have an odd number of negative signs, and this would be a negative. It would totally mess up this expression. So, but okay, so we've shown that for any 4k plus 1 prime, there is we found an A such that A squared is congruent to -1 mod p. All right. This is the last slide here. Wow. Okay. Now, okay, now we have a P and an A, and I think I maybe misspoke myself, because we're going to use Thue's lemma, and we're going to use this A as our A for the, maybe it is the same A actually, sorry, I think. So, okay, so we have this, we have this A squared is congruent to -1. All right, now, just to reiterate the lemma here, Thue's lemma, for any prime P and for any A not a multiple of P, okay, we can find an X and a Y in this range, and both X and Y are, notice, both X and Y are less than the square root of P, and that's important. All right, so either AX is congruent to plus Y or negative Y, all right. Okay, so now we have A squared is congruent to -1, we'll multiply both sides by X squared, and this X comes from here. So we have A squared X squared is congruent to negative X squared. We just multiply both sides by X squared. But A squared X squared is simply is congruent to Y squared. We just square both sides here, right? So we can substitute that. So we have Y squared is congruent to negative X squared mod P, and we bring over the X, and we see this, which is, we're almost there, right? X squared plus Y squared is a multiple of P. It's congruent to 0 mod P. But we have to show that it's actually P itself and not some other multiple of P, okay? The way we show that is simple. It's quite simple. We know that X is less than the square root of P, and so is Y. So X squared is less than P, and Y squared is less than P. So X squared plus Y squared has to be less than 2P, right? And it's pretty clear that it's not equal to 0, because these cannot be 0. Anyway, okay, so if it's less than 2P and it's a multiple of P, the only remaining possibility is that it's P itself. So I think that takes care of it. So did I lose anybody recently or anything? That's pretty much the path of this, how this way of proving it, which I thought was really neat. At least I sort of basically understand it. So that's pretty much it. So thanks for bearing with me.